Hi everyone. Just to make sure, can you hear my voice and see the slide on the screen?
Yes, we can see it clearly.
Okay, thank you. So immediately we will start. Okay, we will start right now. So hi everyone. Before we start, let me introduce myself. My name is Riyansyah. Me and Christian will be presenter for this workshop. Thank you for joining this fourth geometallurgical workshop. This workshop has been attended from diverse backgrounds, from geologists, metallurgists, geometallurgists, geotech engineer, and mining engineer. The past participants were from Asia, Africa, Australia, North America, as well as Latin America. So thank you for showing your interest, and thank you for sharing the information about this event as well. As we know together, now we are on fourth event. If you are interested on part 1, part 2, and part 3, and you missed those parts, you can watch it on YouTube. We have uploaded it. Just search Mining Geology Talk. We have made a playlist on the YouTube consists of part 1, part 2, and part 3 respectively. Just search Mining Geology Talk. Here is my profile. I'm a geologist currently working for Sumbawa Timur Mining, an Indonesian. This is subsidiary of Vale, an Indonesian company. I am fluent in mining geology, geotechnical engineering, geostatistics, and data analysis. If you are interested to connect with me, I can be reached through LinkedIn on this link, Abdul Riyansyah Parinduri. And this is Christian profile. I think Christian is here already. Hi, Christian. Can you hear my voice?
Yes, yes, my friend.
Hola, mi amigo. ¿Cómo estás?
Hola.
Hola. Are you ready for our session?
Yes.
Okay.
Ready?
That's really great. So yeah, so far we have 23 participants or attendants. Yeah, Christian is a professional with more than 20 years experience. His specialization is in geological and geometallurgical modeling. He is fluent in project development, audit, consulting, and technical reporting, as well as machine learning. This is our agenda. We have just finished the opening, and I will present the recap from part 1, part 2, and part 3, just to make sure this fourth part is aligned with our previous sessions. And I also will briefly explain about layout for this session, and Christian will present the case study. We will have 10 minutes for question and answer, as well as discussion. If you have questions, you can turn the microphone on during the Q&A session or simply type in the chat section. Then me or Christian can read it. This is our recap for part 1. In part 1, we talk about geometallurgy can be started in any stages during project development since scoping study to operation stage. What is the difference during each stages? The difference is on the accuracy of the project. Precision and accuracy will increase during the stage. It means during the scoping study, it's not necessarily we define exactly the right geometallurgical domain. the thing that we need to do during the scoping study is we identify what is the potential variable that might impacting our comminution stage or mineral processing stage. And then as we move to higher stages like pre-feasibility study, feasibility study, and operation, it requires higher precision and accuracy. Increase on higher increase of precision and accuracy, it will affecting or impacting the budget and expenditure for the geometallurgical campaign. Generally speaking, from geology to block model, these stages are quite similar to those used in grade estimation or geotechnical parameter estimation. The first thing that we need to do is we ensure we conduct a proper sampling program, and then we do the analytical work using or laboratory work, and then we define a model or domain using this approach, exploratory data analysis, using data analysis or machine learning, and then at the end we will estimate that parameters and then put it on the block model. Yeah, this is recap for part 2, defining geometallurgical unit. Based on EDA result that we conduct, result of geometallurgical testing of sample from different domain will permit the generation of GMUs. In this slide, GMUs 1, GMUs 2, and GMUs 3. Finally, estimation is required for interpolating values of the parameter in the block model. So it will be critical we combine our geological unit, either lithological, mean zones, alteration, geomechanics, and other geological units, and combine with metallurgical tests with help from data analysis or data mining or machine learning method. So in that sense, if we want to conduct this geometallurgical unit, we need to fluent on that aspect as well about the data analysis. Yeah. This is the exploratory data analysis. Hola? Yeah, this is exploratory data analysis. Yeah. In exploratory data analysis plays important role for the domaining stages, as I said before. This graph informs us about combination of 3 aspects to perform proper exploratory data analysis. A well-organized data collection will help us to provide data with minimum of treatment before we process our data. And also, if we have good or well-organized data collection, we will not lose our precious data if the QA/QC program of our data conducted properly. After we have removing outlier and
Man, you are mute.
yeah, thank you. So wait a minute. I think someone share the screen.
Yeah, maybe.
Dynasty Hadian.
Me. Sorry.
Okay, no worries.
No, not me.
Dynasty Hadian, can you turn off the screen? Okay.
You can just.
Yeah, I'm doing it right now. I'm doing it right now. Please wait a moment.
Still watching this screen.
Yeah, we are. I'm uploading it again. How about now? Can you see the screen?
Yeah.
Yes.
Yes.
Yeah. Okay, thank you. So we are on machine learning, right? So yeah, a well-organized data collection will help us to provide data with minimum of treatment before we process our data. And also we will not lose our precious data if the QA/QC program of our data conducted properly. After we have removing outlier and other data cleaning method, etc., we can perform statistical analysis to our data, either descriptive or predictive statistics. During this stage, we can use various types of statistical methods, such as neural network, k-mean clustering, hierarchical clustering, regression tree, etc. Using the algorithm mentioned above, we can generate a machine learning for our geometallurgical program, which consists of train and testing. It will automatically improve through addition of new data. This is recap of part 3, estimation of geometallurgical parameters. In the session, we talk about what kind of method we should use for our data. Of course, there is such a temptation to use kriging to estimate our geometallurgical parameters because kriging is such a fancy way to estimate our parameters. Unfortunately, not every data can be estimated using kriging because kriging uses kind of assumptions such as stationarity as well as spatial relationship. If your data doesn't have that kind of assumptions, proxy could be the other options. We can easily obtain a number of variables using singular or multiple linear regressions. If we have strong correlation which expressed by coefficient of correlation. But if we have poor correlation and low amount of data, imputation could be the option by replacing or filling the data with mean or median value. As indicated on the arrow on the bottom of this slide, geostatistical methods tend to require a required number of samples and then high cost, and then if we have pre-feasibility or feasibility study, of course it will necessary if we have proper amount of data, and then so we can use that geostatistical method. But if we in the early stage of our project, it's not necessarily to estimate our parameters using geostatistical approach, kriging, inverse distance, co-estimator, etc. We can just use proxy or imputation. I bet some of us very familiar with this image, since majority of us is working for mineral industries. In case you are not familiar with mineral processing stage or workflow, this slide is showing where our study case taking place. The study case will take place at this orange box on concentrating stages. Generally speaking, we have two options to process our metal based on type of the ore defined by geologists. The first one, through concentrating, as indicated on the orange box. And the other one is through leaching. The workflow shows comminution stage, which reducing in particle of our material on process into ore. The idea here is to liberate our metal from the contamination. Of course, in the real world or in the real plant, between sack mill and ball mill, we have a cyclone to ensure the particle size that sent to ball mill is on the proper size. The detail of sack mill, ball mill, and flotation circuit, and the particle that produced from sack mill and ball mill will mentioned by Cristian during his presentation session. And this is our roadmap. Firstly, we will consider a definition for geometallurgy as well as drivers that promote this discipline and its importance in mining industries. Secondly, we are going to review the stage of constructing of geometallurgical model. Then we are going to establish the relation between geometallurgy and resource and reserves. After this, we will describe the requirement of geometallurgy by each project level of study. Finally, we will discuss 4 study cases with specific application of geometallurgy. Okay, Cristian.
Abdul?
Yeah.
Sorry.
Yeah. Yes, please.
Sorry, man.
Yeah.
I'm running a different roadmap. Just in case, I check the control from now.
Yes, please.
Okay.
You can take the control from now. Okay. Before we start,
yeah, I will let you repeat this slide because yeah.
Yeah. Before you start, can the participants, can you confirm that Cristian's voice is clear? Cristian, can you talk, please?
Yes.
Yeah.
Yes.
Okay. Cool.
Yeah, it's clear.
Because I think in
Hello. Hello.
Not really clear on my
Okay,
side.
perfect.
Okay.
Wanna get closer to the microphone? Just
okay.
Okay, so I will control of the presentation. This is the 2. Okay, so can you see the no? Hello? Hello? Can you hear me?
No veo nada, Cristian.
Yeah, that's clear.
Wait a minute. Can you see now my screen?
Yeah, we can see your screen now.
Yeah. Gonzalo, can you see my screen?
Sí, sí lo veo, Cristian, se ve.
Oh, okay. Excellent. Okay, now Okay, this is our roadmap for session. And here, okay. We want to review after the recap from Abdul. We want to review firstly the description of our study case. This is our last session with this study case. We want to start by the description of this study case. Afterwards, defining the process, then a base case. Then we're going to evaluate the impact on mining plan. After this, implementation of geometallurgical model. And finally, a re-evaluation of the impact of them in the mining plan. So, next. Okay, let's start with the study case description. The study case corresponds to an open pit mine with an annual using samples from exploration drift. A metallurgical campaign was conducted. These samples were tested to obtain the comminution parameter work index. Based ball mill specific energy consumption was determined. Okay. The study case timeline comprises a 10 years life of mine plan. A metallurgical campaign was developed 3 years before the operation started. Sorry, Abdul, maybe can you turn off your microphone for a while?
Yeah, sorry.
Okay. So a metallurgical campaign was developed 3 years before the operation starts. The block model of the deposit was populated with a estimation ball mill specific energy consumption. Finally, for validating the block model in year 1 of operation, a geometallurgical campaign using drill core samples was carried out. Okay, defining processing variable. Work index, our variable, in a sample from 1 to 0.1 millimeters using a laboratory ball mill, according to the standard test defined by Bond. Work index allows the estimation of industrial ball mill energy consumption. Okay, but an important question arises. Is work index a reproducible, internationally accepted test for geometallurgical characterization? What do you think? Okay, the answer of this question is yes, indeed. Work index is probably the most used and accepted comminution parameter. Established metallurgical testing for geometallurgical characterization. Okay, let's continue. Our base case, samples from exploration drift. The figure represents a schematical section of the deposit, displaying years 5 and 10 of the mining plan. Year 10 is the life of mine, are shown in the first collect from the sample 1, 2, 3. Over these 4 samples, multiple metallurgical laboratories were conducted, including the 4 work index shown in the section. These results. To bear in mind, the upper yellow zone is located above the top of sulfates. This is the top of sulfates, okay? This is dashed line. The top of has of voids, and as you see in the picture, the lower red zone is situated beneath the top of sulfates and typically exhibits low amount of voids and fractures. So, regarding these are the samples. This is a question for you. Okay. Let's move to the next one. So, our base case, samples from exploration drift. As the laboratory test results display low variability, this is the results. The block model was in which working, that is to say, 13.8 kilowatt hour per ton. So here we have the block model imputed with the value. As we can see, the loan plan life index parameter. Okay. Now let's check the plant layout. The diagram displays the plant layout for the copper grade for the plant's feed is 1% of copper, okay, and with a 90% of metallurgical recovery. Okay, this is case. After primary crushing, a SAG mill allows, this is the SAG mill, allows the reduction of material to 80%. Then 2 ball mills must reduce the material at 210 micrometers for the flotation process. Remember the words of Abdul. This is a requirement, the granulometry, for the flotation process for appropriate liberation of sulfates. Good. So now let's calculate the throughput in tons per hour to reach this metal production. The metal production is 100,000 tons of copper by year. Tons is to be useful for afterward calculations. Okay, firstly, annual copper production depends on tons per year, or TPY, by copper grade by metallurgical recovery. Okay? Now, tons per year can be expressed as tons per hour, or TPH, by 24 hours in a day, yes, by 365 days in a year. Then, isolating the tons per hour, we can obtain the results of TPH, tons per hour, for the ball mills, is 1,250 tons. With this figure, with this number, we can reach this annual production, considering our grade, the grade of this and the metallurgical recovery. Well, okay, 1,250. A question for the project: what was the electric power required by ball mills, considering our work index? This is the value we have in the block model. All the blocks have this value. Okay. Let's ball mill capacity. This equation developed by Fred Bond. This equation can also be expressed this. Okay. Where equation W, okay, is the ball mill specific energy consumption. WI is the work index in kilowatt hour per ton. This number 100 micrometers, the product size in work index definition. And the parameters P80 and F80. 80% passing side, feed F, and product P. This P80 and F80 is F. Okay. Good. Let's replace the variables with the values of the study case. Work index from the block model is 13.8. P80 is 210 micrometers, where F80 is 2 centimeters or 20,000 micrometers. In addition, we have this 0.95, which is the availability factor. Availability factor represents the probability that ball mills operate with the average. We don't have all the time the ball mill operating. So this is the factor for correct this. Assumption for the 2 ball mills is 8.1 kilowatt hour. So good. Now we have the specific our ball mills. Good. Return to the plane scheme. Same. Now let's calculate the electric power required for the 2 ball mills. Electric power is equal to tons per hour by the specific energy of all of ball mills. So we have for that it is required a throughput of 1,250 tons per hour. The specific energy consumption of the ore is 8.1 kilowatt hour per ton. Then the 2 ball mills of 5,000 kilowatt hour are required to achieve a throughput of 100. This would allow a production of 100,000 tons of copper. Okay, so now we have this ball mill power requirement. Okay, so we are after the starting of the plant. We are in the year 1. So what is happening currently? The plant is already operating, working on combination process state. Today, ball mills are working as planned with a steady behavior of the material in terms of hardness or energy consumption. This maintenance is carried out as scheduled. So this is important. We are satisfied with the throughput model. What can go wrong? So everybody's happy here. Manager is happy. The metallurgical engineers are happy. Geologists, miners, all people is happy in this company. So what can go wrong? And in this moment, I would like to make a stop and ask, and I would like to any idea. You think you're okay? We are okay? Not as it looks.
Yeah, I think if we have different geological condition, it will impacting the value of bone work index for each material. So in that sense, it will affecting the process in the SAG mill and ball mill.
Yeah, could be, but you need to speak up because you need to face the manager. You need the manager of the plant, the general manager of the mine. All these people be happy with this model. So, okay, let's see what could go wrong? Let's see. Let's move forward. Remember, we are operating. We spent a year operating, and Abdul in the mind was saying, okay, maybe we need to make a confirmation of this model. So let's do this geometallurgical implementation. Okay, good. And for confirming the work index model, a geometallurgical campaign was conducted. So for this geometallurgical campaign, something going to be quite different from the samples from the drill exploration. Firstly, we want to have a regular distribution in the space of the samples throughout the LOM, throughout the mining plan. The sample is going to be collected from cores. Each work index test will be developed on an individual sample. No mixing. It's not a core interval. So samples were to be tested. So what could happen here? Let's come back to our slide after geometallurgical implementation. Now we have this operating mine, and let's display in our schematical section the work index for the geometallurgical campaign, including the exploration drift. Remember the exploration drift? This is the exploration drift. It is observed, as you can see, that, remember the yellow one, work index values are below 14. These light blue and blue rectangles. On the other hand, in the lower zone, the red zone, samples show work index over 14. Wow, this is what happened in the red rectangle. Oh, this is interesting. And the question for us is, can we identify any geological control on the work index results? Do we have a geologic figure here that can explain this behavior, this contrast? What do you think? Okay, let's move to the next one. Good. Impact on mining plan of this thing. Work index. Let's evaluate the changes of work index by year in the mining plan. This is the mining plan from 1 to year 10. We are make this comparison from this base case developed with the exploration drift samples, the orange columns, remember, this constant value, compared with the mining plan after the geometallurgical implementation, the blue columns. This is by year. These are the numbers by year. As we can see, it is recognized a significant increase of work index from year 6 onwards. Now, the question, my dears, is what might be the impact of this significant increment of hardness on throughput? What might be? Okay, let's check this. Impact on mining plan, this time in throughput. Let's evaluate the changes of throughput by year in the mining plan, comparing the base case developed with the exploration drift samples, the orange columns, and the mining plan after the geometallurgical implementation, the blue columns. It is recognized a decrease of throughput from year 6 onwards. Now, the question is, what could be the impact of this significant reduction of throughput on the business? What could be? Let's see. Impact on copper production. Now let's evaluate the changes of copper production by year in the mining plan, comparing the base case developed with the exploration drift samples, the orange columns again, and the mining plan after the geometallurgical implementation, the blue columns. It is recognized a decline of copper production from year 6 onwards. Indeed, copper production is reduced from almost 1 million to 877,000 tons, with 12% less of metal produced. A significant reduction, as we can see. Finally, this is the impact on mining plan considering the financial point of view. The evaluation of the changes of metal value by year in the mining plan permits to recognize a reduction of metal value from year 6 onwards. The metal present value is reduced from 1.51 to $1.45 billion, with 4% of value reduction. For this calculation is used a 5.5 interest rate. So, what is the conclusion of this study case? How can we link our study case with this journey of 4 workshops, almost a year of enjoying together these wonderful topics? Conclusions. Firstly, it is important to clearly understand how geological features impact the different stages of mineral processing. In our study case, the top of sulfate is a key parameter. Secondly, fluent communication between different units in the mining company, as well as discussion about parameters that potentially will impact the operation, are crucial activities for a successful geometallurgical program. Thirdly, sampling is a key matter in geometallurgical characterization. Representativity of sampling in drilling campaign based on adequate spatial distribution in the mining plan is also a key aspect to bear in mind. As we can see, geometallurgy has a significant influence on the mining business. For our study case, differences of 12% in metal and 4% of metal present value are recognized. Finally, geometallurgical implementation is a powerful tool for reducing risk and identify opportunities in mining projects. Okay, guys, after these 4 sessions, after this almost a year of pandemics, and Abdul and I want to thank all the participants of this workshop and the previous workshops. Thanks. Terima kasih banyak. Gracias.
Yeah, muchas gracias, mi amigo. So we have question and answer for like 10 minutes. If you have a question, please turn your microphone on, or you can type on the chat section. So please. Okay, Christian, while we are waiting for a question, in your opinion, in terms of geometallurgical sampling, what is the minimum requirement of weight? Should we use this GIS formula or something as a guidance for our geometallurgical sample weight? What do you think? Hola, Christian, can you hear my voice?
Sorry, I was in mute. Okay.
Okay.
Yeah. Now I proceed to answer the question as good as. I'm gonna try to do this because it's a tricky question. It's a good but tricky question.
Yeah.
Honestly, never used the Pierre-Gis equation for geometallurgical sampling. I'm not sure if I see this equation applies in geometallurgical sampling, but about the size or weight, it's depends on at least 2 things. The first one is the number of tests we want to conduct, the requirement of mass of each test, and last but not least is the particle size, because there are some tests like SMC, which is similar to drop weight test. It's the short version of a drop weight test that require, shall we say, a core of HQ diameter. I don't know if all of you are familiarized with HQ. HQ is like diameter of 6.4 centimeters, more or less. Not, and if we can use NQ, for instance, like less than 5 centimeters for SMC testing, which is a comminution test, like bond work index. So the answer for your question is depends on the number of testing you want to conduct, the mass requirement, and the particle size. But as a general rule, I can say between, if we have several tests, between 30 and 60 kilograms. 30 to 60 kilograms for including several testing, like flotation, comminution, environmental, and others. That's it.
Okay, excellent. Thank you. I think we have a question here from Fahma. Fahma asked about, is it geomet only about comminution and acid consumption, or is there anything else? And the second question is, I heard once about boron penalty related to concentrate export. Can you explain what is that? Yeah, that's a question from Fahma. Thank you, Fahma.
Thank you. The second question was about a specific element. Sorry, man, I couldn't hear clearly.
Okay.
Second one.
Yeah, I will repeat it again, but if it's not clear enough, you can read it on the chat section. Okay. So the second one is, I heard once about boron penalty related to concentrate export. Can you explain what is that?
Yeah, I am reading now. Yeah, thank you, Fama. Thank you. Yeah, I'm reading the questions. Well, the first one, is geomet only about comminution and acid consumption? The answer is no. Actually, considering the parameters for geometallurgical characterization, is any parameter that could affect processing, even for mining, for extraction, for hauling, like for instance PM10, which is a particle material 10 micrometer. Maybe you have heard about it. It's for environmental. Why geomet? Because geomet is trying to put in the block model any parameter that could affect the processing. If you are producing a large amount of PM10, the authority can just shut down your business, you know? And this is nothing to do with the plant. It's before the plant. It's when we blast the material in the open pit, for instance. So it's about, there's so many variables. I'm gonna try to list some of them. PMT, for comminution, we have several of them. In flotation, in thickening, it's really important thing. We need to characterize the mineralogy of our, if you have phyllosilicate, we have clays, what type of clays? Not all the clays respond the same in the thickener to obtain clear water. And for damp material, for acid generation in the dumps, in the tails. Other example is about your second question. It's about the penalties in the concentrate. Yes, I'm not really sure about boron, but use or typical contamination or penalties are related with arsenic. For instance, over 3,000 ppm or 0.3% of arsenic, you're gonna be punished, you know. So your concentrate going to the buyer going to pay less for your concentrate because you have to pay a penalty, as you said, in good, for the arsenic concentration, the antimony, the mercury. It's really, really good, important thing, and not only for the penalties, because be careful, because all the maritime, I don't know, the ships in the next, probably in the future to come, the ships not going to be able to transport material with high mercury or arsenic concentration. So it's very important. Your second question. You ask for an explanation. The explanation is that when we produce this concentrate, unfortunately, if our these not desirable elements as arsenic or boron, maybe mercury, antimony, are present in the sulfides, so unfortunately we want to increase concentrate as well with the copper or nickel, these undesirable material elements, and this is going to be a important issue for your marketing. So if we are in a very early stage, even in exploration, we can just think about it and think, oh, wait, where is our copper? What is the department of the copper? Ah, it's only in energite. Oh, wait, energite, arsenic. So we need to think about processing material from the early stage of the projects.
Okay, that's really excellent answer, Christian. So is that clear enough, Fahma, or you want to ask more about it or something? Fahma?
Fama wrote in the chat. It's okay.
Okay, so it seems your answer is answering his question. So is there anything? Yeah, no worries, Fahma. No worries. So there is another question again. Is there any other question again? Okay, Christian, I think Fahma asked another question. How the geometallurgy related to petrography?
Wow, this is a really, really good question. Okay, man. This is an excellent question. Yeah. It's could be really important. Actually, as we know, in terms of physics, in terms of geomechanics, we can have, imagine we can have same lithological composition, for instance, granite, but we have maybe 2 units of granite, same deposit. One is a fine-grained granite and the other is coarse. Probably in that case, because of the size of the grains, the finer granite going to be harder. So the energy consumption for crushing, for milling, going to be higher than the coarse granite. Why? It's a physical process. as far as I understand, is because each crackle you create, you produce with the milling, find more contacts between the grains. For instance, in 1 centimeter of the fine grain, going to present more contacts. So the pass of this energy, mechanical energy, going to be more difficult. And then the finer the grain, the higher the energy consumption, even with the same petrological composition. So about your question, yes, petrography could be an important indicator for energy consumption. And the importance of energy consumption is high because usually at least 40 or 50% of the cost, operational cost in a mine, in a concentrator mine, it's energy. So it's really, really important matter.
Okay, thank you, Christian. We have another question from Roberto. How influence the work index in the geological modeling or geometallurgical modeling?
Okay. Okay. How influence the work index in the geological modeling? Yeah. That's a really good question indeed, because when this is typical, when we think as I'm a geologist, okay? Usually geologists, we consider or think geological model for control the grades, gold, nickel, copper, coal, whatever, okay? So it's important that geologists understand that grades are not the only parameter for modeling. We need to think how our alteration, lithology or mean zones can affect the process. So how influence the geological model? Influence the geological model because there are more parameters than grades, and the geologists needs to bear in mind that. And about geometallurgical model, the work index is, well, we need to define proper units in the geometallurgical modeling for work index. And remember, as we checked previously, maybe we want to have some geometallurgical or geological combinations for create geometallurgical units for work index, but maybe other for metallurgical recovery. Okay, so they are not necessarily the same. Actually, usually are different. And Ikrar has another question. Hi, Christian. Based on your experience, what metallurgical test that is effective to define the ore type? The ore type, recovery, lime consumption, cyanide consumption, that will be used to estimate geometallurgical model in gold deposits. Okay.
Yeah, Ikrar is a person who consistently attend our session since part 1, part 2, and part 3. And then, yeah, he's showing really highly interested. Yeah, highly interested for our workshop.
Yeah, and I think it's difficult to answer, but maybe it depends on the impact. Maybe recovery is not the most important parameter in your operation, because maybe recovery is steady. And maybe land consumption is really variable. Or the cyanide consumption, because we have other species like zinc or copper, is variable and even high in some specific parts of our deposit. So what is the most important in gold depends on the variability of these parameters, or shall we say, what is the variable that impact in the highest manner the operation. So typically is recovery, but maybe not necessarily always recovery. Okay, but if I have to take one, I could say recovery. Okay, but not necessarily. That's to bear in mind. Okay, and Elizabeth is asking about what criteria do you use to decide the amount of samples for the geometallurgical modeling? Well, this is an excellent and question. This is a really good question. This is a really big thing in geometallurgy. In my opinion, this is a not very understand problem. Sampling, amount of samples. We are working nowadays in that matter. I would say that in the beginning of the projects, maybe we should take not many samples, okay? And when we move from, for instance, scoping to PFS, this is the point we need to decide the amount of samples. In scoping, maybe it's not really important, as Abdul explained, maybe in scoping study, early stage of the project, we can have an average of, I don't know, 5-10 samples. It's maybe okay. But when we move to PFS, we need to think about the amount of samples. Probably, as a rule of thumb, statistical rule of thumb, we need to have between 20 to 30 samples, okay? This is a statistical criteria, 20 to 30 samples by important unit, okay? This is the recommendation. But when we move to FS feasibility study, we need to increase the number of samples. In that case, we can consider a different approach. If we maybe I could, I don't know if good, we can maybe display the, no, maybe not. I just want to say we need to have these 20 to 30 samples in PFS. When we move to FS, feasibility study, then we can make some more advanced studies like variography to understand how many samples do we have. We need to take for proper confidence in our model. I would like to say that there are other approach to this, like panels. This is a good approach as well. In the panels, for panels, I can think in the next manner. I'm gonna take one sample for 2 million tons of production. Okay, for instance, if my plant is 100,000 TPD, so I can say, oh, okay, I'm going to take one sample by 2 weeks of production for feasibility study. This is okay, maybe. Okay. So there are different approaches. There are not, unfortunately, a rule. And we have talked about this in the previous workshop, which is available in YouTube. Okay. Thank you, Elizabeth, for the question. And Javier?
Yes, Christian, I think, yeah, thank you for your answer. Question from Apun will be our last question.
Okay.
Yes, so we have Javier and Apun Permana, okay?
Okay.
Thank you.
Thank you. Okay. Okay, Javier asking if sampling is a key matter and the number of samples is very important. The answer is get proxy test for deposit. Yes, this is a really good comment of Javier. Yes, excellent. Thank you. Yes, Elizabeth and everyone, maybe we can just take 20 to 30 samples and test the correlation of these results with a variable with more amount of samples, such as assay, geomechanics, mineralogy, logging. So maybe we can make a regression, okay, for work index using mineralogy or using ICP or XRF. Why not? So this is a really good approach, Javier is saying, for avoid taking thousands of samples. Maybe it's really good, but it's really expensive. And proxy is a really good option if, as Abdul shown, if we have a good correlation between the variables, the predictors, mineralogy, assay, with the function we want to, or variable we want to predict, such as recovery or work index. Thank you, Javier. And the last question, besides clay is Permana, Apun. It's besides clay, yeah? What is the other mineral can impact to recovery or throughput, and how to reduce the impact? Okay, so what mineral can impact recovery? Okay, actually, recovery is not necessarily impacted by clay, not directly impacted by clay, because clays not interact with sulfides. The problem with clay is other. The problem with clay is usually when we have significant amount of clay in our cell, flotation cell, this, because it's really fine, this stay in the water and can be dragged or pushed by the bubbles. So you can increase the mass of your recovery and decrease the grade of the concentrate. That is the main problem with the clay in flotation. Downstream, there are other problems, but in flotation, clay can go together with sulfate in the concentrate and decrease the quality of our concentrate. This is bad. But maybe limonite iron oxides are worse than clay for flotation, because you remember flotation is a physicochemical, for that reason, process, for that reason is a surface phenomenon. And if we have a really thin layer of limonite over a chalcopyrite, the flotation ability of this chalcopyrite is going to be reduced dramatically. Okay, so maybe limonite is worse than clay for flotation. And for throughput, even clay can be used, can be good for throughput in some cases because it's softer. Not necessarily clay means reduction of throughput. And other mineral, yes, maybe feldspar or other hard minerals can reduce the or increase the energy consumption or the capacity of the throughput capacity of our mills. And we have a last question.
I think if we have another question.
Yeah, maybe the last one.
Yeah, I think if you have another question, you can send it or ask it through LinkedIn to Cristian profile or my profile.
Okay.
Yeah.
Good.
Okay, so yeah, I recognize we still have several questions here, but the time is finished now. So I think yeah, if once again, if you have another question, please reach us through LinkedIn, through to my LinkedIn profile or Cristian's profile. Yeah, and for the last, me and Cristian really want to say thank you for all of you who participates since part 1, part 2, part 3, and even this last part. And thank you for a wonderful year. And yeah, you want to add something, Cristian?
I want to say thank you for joining us, join us in this good activity. Yeah, this nice activity. Thank you all of you. Thank you so much.
Okay, thank you. So in that sense, yeah, in that sense, I will end this workshop and see you on the other occasion, or see you when we see you. Bye-bye.